So previously, right, we were using the small angle, small error analysis method, and we were assuming that everything was going to be linear. But what if it wasn't linear? What if we were dealing with a nonlinear case? Let's see if we can, for a very basic case, when we take that loop filter function back down to being equal to 1 for its transfer function. Let's see what happens if we do some nonlinear analysis. Under this condition, the time domain transfer function is going to be 2b sinc 2 pi bt. Now recall, right, our sinc functions look something like this. And you could kind of think of this as being a very narrow bandpass filter. And it would suppress like higher frequency terms because this doesn't contain as much energy. So we're just actually going to approximate this for this situation. We're going to say that in this case, the filter in time domain is basically going to be an impulse. So if we do that, if we assume that it's an impulse, we can now see that this is going to be an impulse, which makes things easier for us because we can, again, pull those constants to the front, and then we can use that sifting property and basically just simplify this down quite a bit so that all we're really left with is the sign of the phase error difference. And again, we're going to use that same constant related to our phase lock loop thing. So we have this as our output derivative, our output phase derivative. And so this is what would be entering the VCO. Okay, so we have this entering the VCO, some AK sine theta e t entering your VCO. And based on the definition of the error as being the input minus the output, we can also say that the difference in the derivative of the error is the input derivative minus the output derivative. Okay, so therefore, the error here, this is going to be equal to the input minus the output. So we're going to just take this output, put it in here, and we see that the error is equal to the input minus this derivative of the output. Okay, so since we can rewrite the input frequency using the VCO, so this is back to our same old tricks where our input gets, at our input we have some frequency that we have received that's different from the VCO free running frequency, some phase difference that's different. Then if we took the derivative of the input, so using that same input again, we can see that, right, this is constant, this is going to go away, and then this t is also going to go away. So the input derivative is equal to this. So recalling that we just defined the derivative, the error derivative is equal to the input derivative minus the output derivative. Now we can substitute this into here and arrive at a final expression for the derivative of the error. So what is the meaning of the derivative of the error? So the meaning of this is that when the derivative of the error is equal to 0, the amount of error is not changing. So this is what we want. We want this to be, we want to have the case where those functions are locked, right? So that the phase difference doesn't change no matter where you are in time, right? That's phase locked. So this is the desired case, is that we want the derivative of the error to be equal to 0. And this means that there's a constant difference in the incoming phase and the VCO phase. That would be this constant. So when those are constant and it stays constant, we know that the phase is locked, and we know that the frequency is the same. We know that our VCO is now generating a frequency that's the same as what we received. So we want that to be 0 or a constant. So we want the error to be a constant, and we want the derivative of the error to be 0. Okay, so let's take a look then at an example, right, where we have the derivative of the error here for this nonlinear case. And we, based on our analysis, we saw that this is the input phase and the output phase. And so this is going to be some sinusoidal voltage that can move, or sinusoidal signal that can move up and down based on the difference between the received frequency and the VCO frequency, and also on those constants related to your phase lock loop. So if in this example, if you had a incoming frequency of omega naught equals 10 and your phase lock loop runs at 9.5, then the difference between those two is pretty small to begin with, half a hertz. And we can see that that half a hertz is reflected here, where we have the difference in these two minus AK, because I have AK set is equal to 0. Now in the general case, what we actually need to do is require that the difference between these two is less than AK. So the difference between your incoming frequency and your VCO frequency must be less than your AK constant. Now, why would that be the case? Let's look at the case where the difference is higher. Well, when the difference is higher, in this case, right, this is 1.5, and this is larger than AK is equal to 1. And in this case, we've shifted this whole sinusoid up. It's the whole thing now, right, is above 0. Now recall what we said, right? The requirement is that the derivative of the error must be 0 in order for us to lock that frequency, lock that phase. So if the difference, right, if your incoming frequency is too different from your VCO, then you will arrive at a case where you actually can't lock in that frequency. There's no place where you'll have the error not changing. Your error will always be changing. You'll always be having slightly different frequencies and phase differences between your incoming signal and your VCO output. A little bit furthermore, right, if you do have the case, right, where you had your incoming frequency and your VCO frequency small enough, there's going to be many points where it crosses 0. And then these two, the ones shown in green, these ones are going to be the stable points, and the other ones are going to be unstable. So it would, if there's any perturbation at this point, it'll just move on to one of the stable ones. But the stable ones are stable phase lock positions. So if we were to solve that, right, if we were going to solve for the derivative of the phase error, right, so basically just take the derivative of this and solve for it, we can then rearrange, move that sign over, and see that the sign of that phase error is equal to the difference between those frequencies and AK. And then if we recall our small error, where sine of theta is about equal to theta, we can see that the error, this, right, it would be approximately equal to this when this is small. And so that's the same as our previous analysis when we assumed that the system was going to be linear. So let's kind of summarize a few things. So low order phase lock loops are very simple. They're going to have constant phase error. We saw that constant phase error show up when we did linear analysis and nonlinear analysis. They're going to have a limited lock range, right? You need your incoming frequency and your VCO frequency to be pretty close to the same, and they should be stable within a range. However, higher order phase lock loops are going to be more complex. You're going to require more complex circuitry, maybe multi-stage circuitry. There is the potential to have zero phase error. So the low order has constant phase error. Higher order ones potentially have zero phase error. However, the price for the zero phase error is instability. And there's possible ways to improve it. With the higher order phase lock loops, you might be able to increase lock range or robustness to changes in that frequency if this is changing in time. But it all is going to come at the expense of instability, which is a bit beyond this course, but just know that this is the difference between the low order and the high order loops. And so the concluding note is that we would call the system being phase coherent or in phase lock when your input is the same as your VCO. So once you get your VCO output, when your VCO output is able to return something that looks like this, plus maybe some other constant, right? This would be, we could call it phase coherent or in phase lock. And there is a limited range of omega naught inputs for which we can lock. And that was what we saw in this plot where we had moved it too far up, right? When our incoming frequency is too different from the VCO frequency, you can't get a good lock. So there's a limited range for which you can lock, and this is the requirement for that. So the absolute value of the incoming frequency minus that VCO frequency must be less than those system constants. We call the allowable range, so whatever range of this that you can get to phase coherency or phase lock, we call it the pull-in range or the capture range. So this is some range of frequencies around the VCO. So we have some, our VCO, and there's a limit, right? So in here, we can have our omega naught or omega 0 moving back and forth around some range of the VCO frequency, and it will still be able to get into that range. And we call that the pull-in range or the capture range. And then lastly, the locking may fail if your input frequency is changing too rapidly. And at that point, your VCO would just revert to running at its, normal frequency. This is the most likely the case. So this, hopefully that you learned a lot about phase lock loops. Thank you for sticking with me on this, and I look forward to seeing you in the next series of videos.